Welcome everyone to our webinar on Mastering Quality Control, the power of FT-IR, NIR, and Raman Spectroscopy for pharmacopoeia compliance, which is brought to you today by Bruker. And let me start by introducing our three speakers. We have Mario Eck, a Business Development Manager, FT-IR Spectroscopy, Bruker Germany. We have Dr. Mui Saranwong, NIR and Process Business Development Manager, Southeast Asia and Japan, Bruker Germany. And then we have Dr. Felix Fromm, Application Manager, Handheld and FT Raman, Bruker Germany. We encourage active participation and engagement, so please feel free to ask questions and share your thoughts during the Q&A sessions. Please unmute or use the chat function to place your questions. This session will be recorded, as mentioned before. We thank you for joining us, and we look forward to an enlightening and interactive webinar experience. Over to you, Mario, our first speaker.
Hello, good morning, good afternoon, and welcome to the first part of our webinar today, FT-IR spectroscopy, and how it will help you in the pharma industry and ease your life. So first, the basics, the principle of infrared spectroscopy. What is infrared spectroscopy? It's the studies of the interaction between matter and infrared light. And for this, we take the example of a water molecule consisting of an oxygen and two hydrogen atoms connected with a molecule bond. So now, depending on the energy of the infrared radiation hitting on this molecule, you can trigger special vibrations of this bond. For example, here the symmetric stretching vibration. But there are also others like the antisymmetric stretching vibrations and even a deformation vibration. These vibrations, they are important because this means that the infrared light got absorbed in some extent. So how does this work now? We have our infrared source. This can come from the sun, but usually in our devices, we use like a black body or a center glow bar, for example, consisting of silicon carbide. Now we have this infrared source here, and then the infrared light will hit the sample, whatever you are trying to measure. From there, as I just said, we have the molecule bonds absorbing some of this light. And then we can go even further. We have transmission here, hitting then a detector. The transmission is now the infrared light minus the absorbed light from the sample due to the bonding now vibrating. But obviously, that's simply like a mirror. We also have reflection here, meaning that we can put a detector in for transmission or reflection. And this way we have different possibilities to detect now with a transmission FT-IR, the attenuated total reflection, or a front reflection. Those are more those common ways how to detect infrared light. Now the next part is, I said FT-IR. Meaning this infrared spectroscopy is not only normal infrared, but Fourier transformed. So we have an interferometer in the spectrometers, meaning that we gather all the infrared light and in the end not have a spectrum, but rather this so-called interferogram. So from this, as they rather looks simply almost the same, we don't really have a nice spectrum yet. So now the mathematical equation of the Fourier transformation comes in, meaning after that we receive our reference spectrum, or sometimes more commonly known as a simple background. And the thing, this is something you have to do before every measurement, because as you can already see, this is not a straight line for a background. There's still some absorption, because we have obviously sometimes air, or for the reflection mode, we have a diamond or zinc selenide crystal, which absorbs already some of the infrared light. Now, after we have this background, this reference spectrum, we continue with putting a sample in there. And you can already see here with the before the infrared transformation, we have now already some interference in this spectrum, in this interferogram. And after the Fourier transformation, we already see here are some nice really peaks to be seen in this sample spectrum. And I think now it's already obvious why we choose to have a reference spectrum, a background before that, because now we can simply subtract both and we will receive our transmission spectrum. And here I put a fingerprint because, as I said in the beginning, molecules, depending on their bond, have a different absorption. And as every molecule have different bonds due to their structure, meaning the absorbance is unique for every molecule, resulting in this basically fingerprint for every molecule and atom you want to have. Now, how do we apply this? The applications are, as you can already see here, some pills and substances. But let's start with a simple raw materials and incoming goods inspection. So simply, when you receive your substances before even processing them, you can already check if it's the right molecule, if it's the right substance, because you can have your fingerprint. And from there on, you can already see this is what you are looking for. Then obviously, packaging material. This has also to be checked. For example, that there's the right coating put on the packaging to not interfere with the medicine which is packed into it. Excipients obviously has also been checked, as you only not have your pure medication, but also the excipients. Then after everything is done and everything checked, produced, you have the finished goods inspection. All those can be checked simply and easy with FT-IR spectroscopy. But we are also not stopping there. There's also some possibilities for confirmation checks if you have some proteins. And you can also couple FT-IR spectroscopy with thermogravimetric analysis. This is sometimes also more in the research area. If you want to see how your materials interact, for example, with heat, then you can heat it up in the thermogravimetric analysis, and the gases which are produced during that can be analyzed with FT-IR spectroscopy. So now, the first step, the most prominent one, quality control of a known material. Here you have like different examples of medications, and you can already see that, as I said, the fingerprint, they are all different in nature. Like we start with a benzocanine, then you want to check for this, if this is what and mute yourself if possible. And then if you want to check if this is the right material you want to produce later or work with, then you can apply FT-IR spectroscopy and have two outcomes. The first, obviously, pass the quality control. So this means you get your green check mark and can release the raw material for your production. Or as I said, in the inspection of the finished goods, you can release the final product. Or the other option is that you have to probably have a production stop because it's not the right material you are looking for. And this way you already save time, as you can now, before going into production, put this into the waste back to the supplier. Or if during the finished goods inspection, the test failed, then you can already say, stop the production, don't deliver it, so you don't have to recall later a fault product. So how does the simple operating procedure of such a quality control look like? First, we have the lab manager creating a method. So you can quickly compare those two spectra. Like, for example, we have the glucose monohydrate, as to be seen here. And this way you can already see here it's looking pretty similar. So you can already compare those spectra also percentage-wise, meaning that if the spectra are like 98% similar, then you already can be actually 100% sure that this is the glucose monohydrate you're looking for and can then start production with it. And all those quality control checks are done by the operator. They are the persons directly measuring every day, making sure that the quality stays top and apply the quick measurement method, which was created beforehand. And all this is obviously done then by the software helping to evaluate, meaning you really want to only put your sample on it, start the measurement, and the software will then easily tell you, is it the same product? Will you receive your green check mark and have your finished product? Then, besides the quality control of known materials, which is like the bread and butter of your daily base, we also have quality assurance of unknown materials, which is also an option of which can sometimes happen. As seen here is after the production we have of such a cream, we found a small black particle in it. So this containment can be then easily and quickly separated and analyzed, as it can be seen here, the ATR reflection FT-IR spectroscopy. And from there, we easily can identify this unknown material as an NBR O-ring sealing. So the conclusion would obviously be that a sealing during the production process might have been broken, and you can stop the production and check for where this actually happened. And to really identify this, because we don't have now, like for the verification process, a known material where we can create a method to quickly compare. For this, we probably need a library. And as it can be seen here, this will similar look like this. You have in the library multiple entries, library ID, and also a name of these compounds. So when you put your sample like this little piece of plastic on the ATR crystal, then the system automatically can check of thousands of spectra in this library. And this will roughly look like this. That then you have your unknown material and a reference hit comparing those. And this way, you can also get comprehensive results what your unknown material is actually, like this rubber sealing. So you can, from there on, go for finding the faulty issue in the production process. But also sometimes, as you can also see here, this is not like the perfect fit. Sometimes there are multiple results possible. So experts can also easily identify what of those reference hit you're looking at is the actual compound you want. And obviously, there is the possibility of mixture analysis, meaning the other possibility that this unknown material is not only just one thing, but because it's such difference, that there's also a mixture in it. So this way, with the mixture analysis, you can analyze the compounds on the percentage or the rough percentage, what it's contained of. This can also be applied for your other pharmaceuticals. If you are not looking for exactly one material to verify, but multiple, or want to check if not only what you produce is this one product, but if everything is included. And so I talked about all those software features. But a compliance system, according to the Pharmaceutical Inspection Convention, is like a computerized system consisting not only of the software, but also the spectrometer. Meaning we can break it down here to hardware, software in that regard. And for this, we basically want not only, as I said, a software which is compliant and productive in a way that when you receive your spectra, you easily can continue with your workflow, like have it signed according to CFR 21 Part 11, and which is also part of the compliance of the software, but also really make it easy in your daily work base, and so you don't have to worry about anything. And also, obviously, the hardware has to be compared to the software, choosing the right accessories, like for transmission, which is often used as a requirement in a lot of pharmacopoeia. although the most used method for infrared spectroscopy is the ATR. But that's part of choosing the right accessory and then also working according to the environment. Usually in the production halls, you rather want a robust system compared to a lab. Or depending where you are doing your quality control, even if the lab, you have to switch accordingly, make sure your system is up to the task. And how this can be done and all the things I just explained here. And for this, I want to give a small demo video of one of our products who can be used in the ways I just explained. This is a mobile ATR FT-IR spectrometer. And today I will show you how to utilize this in the pharma quality control. This so-called mobile IR2 is a ruggedized spectrometer. It is connected via Ethernet cable or, depending on the regulations, via Wi-Fi with the ruggedized tablet. We operate the mobile IR with our software Opus Touch, used here on a tablet, but this can also be done on a laptop. Furthermore, we utilize workflows like identification or verification for the quality control. But first, we use the identification workflow. For this, we simply press the button, see if our number of scans is accordingly, and then press the button Measure Background. After the background measurement is done, we simply start with some tablet packaging. We press our packaging on the ATR crystal and fixate it, that we have good pressure on the crystal. Then we again simply press the button Start Measurement. After a quick library search, the material was identified as a blend of different polyvinyl polymers. But in the pharma industry, there are different other materials which needs quality control, not only packaging material. For example, some pastes. So we simply can now put some of this paste on the ATR crystal and don't need to apply pressure now because there's good contact between the diamond crystal and the paste. Now we simply can go to next sample and start the measurement simply again. After a quick library search, again the paste was identified with the main ingredient polyethylene glycol, PEG. Now, to measure the next sample, we need to clean the crystal. For this, we use some isopropanol and a tissue. And carefully wipe off the measured sample, in this case the paste, from the diamond plate. The mobile IR2 is IP65 certified, meaning that spray cleaning, which is an option in some laboratories, is possible, as shown here. After we cleaned the crystal, we now switch to the verification workflow. For this, we simply close the identification and switch to our verification. Again, now we need to measure a background. Simply press Measure Background. After the measurement is done, we now take some aspirin, a well-known painkiller, in this glass vial and see if we can verify it. But first, we take a small amount of powder and place it carefully on the ATR diamond. Then we apply pressure, see if the correct method is chosen, and click on the aspirin. then start verification. Now, after the measurement is done, the aspirin was correctly verified with a green check mark. And again, simply as with the identification, you can continue with the next sample. Or you have the possibility to sign the experiment now. The Mobile IR2 and our routine spectrometer offer a system compliant in software and hardware, making workflows easy in the daily routine applications. And so, see how easy that was? And thank you for attending this demonstration.
Welcome. Thank you, Mario, for the talk on FT-IR spectroscopy. My name is Felix, so I will talk about handheld Raman spectroscopy for quality control, especially in the pharmaceutical industry. So you learn something about infrared spectroscopy, and what we can do with Raman spectroscopy is rather similar. Yeah, we can measure molecular vibration, lattice vibrations, but there's a different underlying physical principle behind. And as you learned in infrared spectroscopy, we are measuring the absorption of IR light, and in Raman spectroscopy, we are basically exciting the sample with monochromatic light of a laser, and we're measuring the inelastic scattered light, meaning the light which, for example, lost some energy because there was some energy deposited in the sample, vibrations had been excited, for example. And in the Raman spectrum, then we see these peaks at the position or at the energy of a vibration. It's a lattice or molecular vibration, and like this, in the same manner, we can use the Raman spectrum for analysis. Depicts a fingerprint like the IR spectrum, you know. So how this is working in practice? Yeah, so it's a rather simple schematic. We have our laser. It's collimated via a lens. Then it's reflected by a beam splitter towards the objective. It's focused on the sample, and then the backscattered light is collected via the same objective. The beam splitter already favors the transmission of the longer wavelength light. With an additional filter, we completely block the Rayleigh, the elastic scattered light, the laser light, so that we are only analyzing the Raman scattered light. Then we focus on the aperture of the spectrometer itself. With the grating, we disperse the light in different wavelengths, and with the 2D CCD detector, we are just taking an image of the Raman spectrum. Here, for example, is just an example of neon light on the detector. And for each neon light at this certain wavelength, we are getting a line. And after integration in bidirection, we get such a nice spectrum. So the same we're doing in a Raman spectrometer. Yeah? It's fairly simple. So the past 15 years, I would say, handheld Raman spectroscopy developed as a standard tool for fast quality control for incoming raw materials. Yeah, so why did this happen? Yeah, it's simple because it's so simple. Yeah, with a handheld spectrometer, most devices include barcode scanners. So you just need to scan the barcode on the packaging. You have the material information in the system. And afterwards, you can do directly the measurement in many cases through packaging material, meaning that you avoid completely, if possible, unpacking in a sampling booth, transfer sample, for example, in the laboratory, so the analysis can be directly performed, for example, at goods receipt or in the warehouse environment. And there's a direct result on the handheld instrument presented of pass-fail. Yeah, either this meets my expected quality of the raw material or not. So today you don't need to be afraid. Yeah, you don't need any longer highly skilled scientists. Yeah, to operate a Raman spectrometer. This had been in the 80s, 90s, so decades ago. So modern touch devices, modern handheld devices, for example, they are all touch operated with guided workflows for maximum ease of use. which minimizes then, of course, operational faults. It's clear, it's all enforced workflows. Of course, the devices today are robust, and fulfill the high uptime requirements of a pharmaceutical production raw materials control. So raw materials control, that's pre-production, and of course there are high workload always to be done. Then with Raman spectroscopy, likewise IR spectroscopy, we have a really high material coverage. We can measure typically mostly solids, liquids, powders, geels, colored materials. So if you just jump into a warehouse or a chemical lab, take all the samples, typically we end up with a material suitability more than 90%. As mentioned before, a big advantage of Raman spectroscopy is the possibility to measure through transparent and semi-transparent packaging, for example, polymer foils, which are commonly used, or glass bottles to store liquids. Additionally to that, the scan times are rather short of vibrational spectroscopy. So with a handheld Raman spectrometer, the typical scan times, depending on the material, are in the range of 10 to 30 seconds. And basically, next to the instrument, there are really low operating costs. We don't have any consumables or employ environmental critical chemicals. So overall, a major cost saving is possible with the instruments. But of course, everything is not always easy. There are challenges. And so the intense laser radiation can as well exhibit or emit or excite fluorescence emission. And for example, here's an example of sodium alginate, where we see a spectrum measured at 785 nanometer excitation, where we just see this slope with some small bumps on top. And we hardly can extract the Raman signals itself. And for example, if we use then excitation in near infrared with 1064 nanometer at a lower photon energy, we avoid emission of the fluorescence and see very clearly the Raman signals. So longer wavelength excitation favors basically the suppression of the fluorescence, whereas with visible excitation, typically is more prone to fluorescence emissions. But why not everybody is using 1064 nanometer? Because there's sensitivity. There's a power of follow, and sensitivity decreases tremendously with longer wavelengths. So of course, then in visible excitation, there are different possibilities to address fluorescence. If we want to say we want to work with visible excitation. For example, there are mathematical data pretreatments, possible, like take derivative spectra or do a baseline correction. But there are as well techniques like sequentially shifted excitation, where we extract basically the Raman signal out of a fluorescence background and get such nice results you can see here with the handheld Raman spectrometer Bravo. So how does SSE basically work? With SSE, we're measuring a series of 3 Raman spectra at slightly different excitation wavelengths. And as the Raman lines are always relative to the laser line, they're shifting a little bit on our detector, which you can see here clearly. Whereas the slope of the fluorescence or any, for example, absorption signals of fluorescence, that's why I've chosen this example, they stay constant. And therefore, with a mathematical algorithm, we can extract the Raman signals and from fluorescence or any background signal, all maintaining high signal to noise ratio. We can clearly distinct the Raman bands, and at the end, we can analyze typically a wider range of materials because of the fluorescence mitigation. That's an example, classical matrix excipient material in pharmaceutical industry, cellulose, where we have already at 800, still at 852 nanometer excitation, we have a significant fluorescence contribution. And just performing a baseline correction, often works, but of course there's always a balance between overcorrecting, which means there might be information loss, or here in this example, it's not fully corrected, and we still have some fluorescence contribution in the lower wavelength range. Going, for example, to FT Raman spectroscopy, which avoids the fluorescence emission because we're measuring at 1064 nanometer. Here we get a really clear spectrum without any contribution of fluorescence signals. And for example, if we compare here a spectra measured with the handheld Raman spectrometer Bravo with SSE, yeah, this fully matches the signature measured with the FT Raman spectrometer, which avoids all this fluorescence. Yeah. So another challenge with handheld instruments, yeah, they are typically rather small. Yeah, so achieving, for example, a large spectral range at a decently good high spectral resolution is typically difficult because there are size restrictions, of course, requirements for high throughput and short acquisition times. Yeah, no one wants to hold this handheld for a very long time at a sample. So with the Bravo, we're employing dual laser technology. So meaning we are using two lasers for our excitation, one laser with 785 nanometer and one with 852 nanometers. With both lasers, we are measuring a spectrum in the same spectral range of wavelength range of the spectrograph. So we are receiving two separate spectra, and we are applying the SSE technology on each spectrum and combine both spectra to get basically this full spectral range from 300 to 3200 wave numbers with the information from the fingerprint and as well information from the CH stretching region around 3000 wave numbers. A next topic I want to address is Raman shift accuracy. Yeah, often the topic was challenging, yeah, in the 80s, 90s with all the instrumentation to achieve good Raman spectroscopy. But I want to emphasize that even with a handheld spectrometer, it's fairly easy as well to achieve an accuracy better than one wave number. So this is shown here in this table based on 20 randomly selected Bravo handheld spectrometers from production and literature band positions of cyclohexane, which are taken from an ASTM reference. Then we have the average band positions from the Bravo spectrometers with a notably low standard deviation of only 0.2 wave numbers. And then we have here the average deviation towards the ASTM reference values. And as you can see, these are really below one wave number. There's a large gap. And if you look now at the pharmacopy guidelines, where the thresholds for the Raman shift accuracy are specified, even with a handheld spectrometer, you can see it's possible to achieve the benchtop requirements, or let's say requirements for quantitative assessment according to the USP pharmacopy. And that's not only important for benchtop instruments or quantitative analysis. Yeah, it's as well important to enable a robust method transfer. For example, what's very typical with handhelds, there's in a technical competence center, the analytical method is set up, the reference spectra are taken, and then this method is supplied, let's say, across multiple sites, is used on different instruments. Yeah? And in this example here, basically, we show the change of the correlation coefficient, if we use a simple correlation-based approach, as function of the deviation in Raman shift accuracy. And already at a change of two wave numbers, we come close to a threshold of 0.95, which is commonly applied. As well, a topic is laser safety. Typically, handheld spectrometers use lasers with up to 500 milliwatt optical output power, classical focusing technologies, and this results usually in a laser class 3B classification. So this implies, for example, personal protective equipment like laser safety glasses. There needs to be a laser safety officer in place in the company. The operators need to receive periodic training. There might be even restriction for areas for operations with safety measures. So with the handheld Raman spectrometer Bravo, we use some beam shaping technologies. We have, of course, output power limits, electronic safety interlock circuits, so that at the end we could certify our instrument as laser class 1 in all operating modes, dropping all above listed requirements for laser safety. A topic as well to address always is IT integration. Yeah? An easy example, 21 CFR, Part 11, data integrity, all these GMP regulations require to store data, of course, in a secure manner. And especially for handhelds, yeah, that's a critical point, yeah, because a handheld typically operates standalone, yeah, so not necessarily it's continuously integrated into a network, yeah, where we have, let's say, live data storage and backup, yeah. So you have to ask yourself, do you consider an electronic record stored in a handheld system as secure? Yeah, the answer is clear. You should not, yeah, because a handheld system could potentially disappear. Yeah, it's clear. So it's very important that you have a modern professional IT integration of such devices, yeah, where, for example, an automatic periodic data backup is enforced, yeah, of all electronic records which are generated on a handheld device. Yeah, these are, for example, then the audit trails on the device, all measurements, including evaluation, so everything which happens actually on the device itself. Yeah? And of course, later on, you want to release your raw materials, so it's important that there's mechanisms existing for automated reporting, for example, to your LIMS systems. So with that, I want to close the presentation and that you get a more clear picture how a handheld Raman spectrometer can be used, how flexible it is. We prepared as well a small video demonstration. Yeah, enjoy it. Welcome, my name is Felix. I'm the product manager for the handheld Raman spectrometer Bravo and our FT-Raman series. Today, I want to give you a brief presentation of our handheld Raman spectrometer, the Bravo, dedicated for pharmaceutical raw materials verification. The Bravo operates standalone, yeah, battery powered with around 4 hours operation time, of course, depending on what kind of samples. It can take around 200 scans with a single charge. The battery simply is exchangeable and thus can be used in multiple shifts in a near continuous operation. The operation is all based on this touchscreen, very easy to use, and the software is all built around compliance to pharmaceutical regulations. Thus, starting the operation of the instrument, of course, we have to log in, we have to authenticate. The device supports multiple user roles to ensure segregation of duty. I have here a small demo account on the equipment, no need for the password, but of course, this can be all user defined. So we can specify password complexity, length, expiration periods, all you're used from a modern user management. In validation mode, the instrument always ensures valid systems tests, which can be performed utilizing certified and traceable reference materials. For example, here in the lower bottom of the screen, you see the screen status indicator indicating that the instrument is ready for a measurement. To start a measurement for raw materials verification, just click on the verification icon to enter the workflow. Here the operator is asked to specify the material information, either using the on-screen keyboard or simple as that, just scan a barcode. Here it's ascorbic acid. Click Next and the instrument will guide the user which measurement tip shall be used. To perform the measurement, just press the sample against the tip and start the measurement. Everything is done fully automated. Depending on the sample type, a measurement takes 10 to 30 seconds approximately, and afterwards the analysis result is displayed. Here, accepted. You've just seen one of the major advantages of a handheld Raman spectrometer. We can perform the analysis directly through packaging material. So there's no need for extracting samples in sampling cabinets and transfer them into a laboratory. The analysis can be directly performed in the warehouse at good receipts prior production. A handheld Raman spectrometer can be employed very versatile. So measurements are not only possible through transparent or semi-transparent packaging foils. For example, we can exchange the measurement adapters. Here, for example, is a tip for measurements in small 4 milliliter vials, but of course we can customize as well adaptations. Measurements in tablets are as well supported. Therefore, we have this measurement adapter here where we can place a tablet on a spring-loaded barrel, just close it and attach it to our handheld spectrometer. This is, for example, an adaptation to measure through thicker walled barriers. For example, through an amber-colored glass bottle. Here I have 1 liter bottle of benzonitrile. I'm just aligning the instrument in front of the bottle, start the verification workflow, specify my material, and press start. Again, the measurement parameters are set fully automated. The measurement just takes a little bit longer because the amber-colored glass induces some absorption effects. So here's the result, accepted, it's benzonitrile included. As a portable device, the Bravo can connect to a Wi-Fi or Ethernet network. For example, to connect to Ethernet, just place it on the docking station and your data will be automatically transferred to a network or server location. During the demonstration, I did not wear any laser safety glasses, so good to know. The Bravo is laser class 1 safe in all operating modes. I hope you liked our small demonstration of the handheld Raman spectrometer Bravo with benchtop performance, which is especially suited for those challenging samples in the pharmaceutical environment, for example, those who exhibit a high fluorescence emission. So, thanks for your audience. I hope you enjoyed it. So, next speaker is Mui, and she will present FT-NIR spectroscopy. Mui, you might share your screen and take over the presentation.
My name is Dr. Mui Saranwong. I'm Thai by nationality and I living in Thailand but work for German headquarters. And I have been working on FT-NIR for 23 years. I will turn off my camera and then I will share my screen and then you can see. All right, today I will talk about 2 things. Of course, NIR also can do identification like FT-IR and Raman, but our focus today is on the quality control, which is the content uniformity, and the process control, or what we so call the PAT, Process Analytical Technologies. Here, you will see that the NIR electromagnetic wave is lying between the mid-IR, which you may be more familiar with, and the visible, where you can see. The NIR is activating the molecule to create the molecular vibration in the same way as the mid-infrared, but it is less sensitive. So this means you can use a thicker samples like 1 centimeter or a few millimeters, and also the sample can have a lot of water inside. How we can measure the spectra in NIR, we can do in both transmission, which is fit for the sample that are liquid samples, either clear or non-clear, and we can measure in reflections, which is fit for powder and solid samples. However, we also can measure transmission in solid samples that are not so big, such as the tablet and the capsule. Here you will see that if we shine the NIR light onto a tablet, some light will be reflected back and some light will transmit it through the samples. When we want to measure the amount of the active pharmaceutical ingredients inside, if we are using the reflections, there is a possibility that the result will not be very precise because there is a coating that block the light to get deep inside, or the light could come only from a few millimeters from the surface. Therefore, we recommend to use transmission through the tablet. Here you have the chemical information of the complete tablet. We can use with coated or uncoated tablet, and the drawback is we need to use a longer measurement time, which takes around 1 minute. It is very important when we measure in transmission that we have a right sample holder because otherwise the light will re-gauge here and reach the detector, resulting in the unprecise or incorrect prediction. So it is very important that you share with us 10 or 20 placebo of each tablet design. Here is how the tablet will be held on the sample holder. This is normally used in the lab for quality control. We have a sample rotator or sample wheel where you can put in up to 30 tablets per time, and then it will do the measurement automatically. On the same machine, we can also measure liquid or solid or things that are in container by fiber optics probes as well. When you look at the spectra in NIR, you don't see much peak like you see in mid-IR because the absorption in NIR regions are highly overlapped, and this is caused by overtone and combination absorptions. However, if we compare this result with the actual HPLC or GC concentration of the API, we can develop a precise calibration model, and then we can use this for the quality control in a much faster way. Let's say you can measure 30 tablets in a matter of an hour instead of waiting days and days for the quality control, and this will lead to the safety of the consumer. Next is the explanation about the process analytical technologies by NIR. As explained earlier, NIR has a benefit because it is less sensitivity, so it can deal with a thick sample like 5 millimeter or 1 centimeter, and it can deal with the sample that has moisture. In the secondary pharmaceutical industry, you have several processes from grinding to mixing, granulation and drying, mixing again, tableting, and coating. And for each point, except grinding, we can implement the NIR or near-infrared spectroscopy to monitor what is going on, and then we can have a production that are very effective and sustainability and environmental friendly because we are using less energy and we produce less waste. Here you see that we collect the spectra of NIR of the sample during the mixing over 45 minutes. We could collect up to 700 spectra, and you can see that in the beginning, when the mixing is under mixing, the spectra are not well together under a certain criteria. But if you mix too long, that could also create a demixing. So the objective of using NIR is to define this position that we can stop the mixing, save the energy and the time, and still have the sample that are very, very well homogeneous. This is the installation of our non-contact probe, where you have the sample coming down here, and we measure every 2 or 3 seconds. And we are using a certain index to identify, and we found that after a certain time, which is only 3 minutes, we can stop the mixing. Next example is for the fluid bed drying. And you can see here that in general, every fluid bed drying or granulation will have this kind of window. We wanted to monitor mainly the moisture content because after a certain time of drying, the sample should be moved to the next procedure. This kind of window can be used as a window that an NIR non-contact head can look into the samples and then can monitor or even give a feedback to the PLC or the DCS to optimize the granulation process. We have 2 possibilities. If the sample are quite sticky and then you cannot have a big window, we can use the immersion probe. You can see at the tip, there is a LED light. The light is coming in and then touch the sample and then reflect it back. We can install a nozzle to clean so we can be sure that we are not measuring the same samples over and over. However, in most In most cases of the fluid bed granulation, there will be a window. We can install this non-contact head that shine the light, and it is totally non-contact to any sample, so you don't have any issue on hygienic. And then we can monitor what is going on in this fluid bed drying without opening the fluid bed dryer. Here is an example. You can see here that when we start the mixing, we spray, drying, and at the end, when everything is good, you can use this kind of information, which is called the conformity index, to decide when to stop the process. This is another publication where the customer is using our probe to monitor the humidity of the sample inside of the fluid bed dryer. Last but not least is the drum coater. Here, what you wanted to do is look like a washing machine. Most of the time is we are coating the tablet with a certain chemicals. We wanted to have the coating not too much and not too less, and we can have this kind of solid probe put inside and the drum is moving. And then we can monitor the growing of the tablet real time, and you can decide when to stop it. On the x-axis is the time that we are using for coating, and then on the y-axis is the coating growth, which is the amount of coating measured by NIR, which is the black dot, and then measured by the chemical analysis, a reference one like HPLC or GC, and this is on the green dot. So you can see it is very, very precise. And that's all from my side. Oh, I have one more slide. Here you can see that here we can have the growing of the coating should be in this upper and lower red dot, and it fits very well. Yeah, and that is all from my side. And NIR, I don't do a video here because most of the time our process analytical technologies are done in customer factory. We cannot do demo on our facility, and these are most of the time super secret. But you can see here that we can have such kind of probe inside your facility, and one machine of us can connect to up to 6 probes, so you don't need to buy 6 machines for 6 measurements. Yeah, thank you. And then I will stop this sharing, and I will return the floor to Felix for the compliance.
Yeah, thank you very much, Mui. Welcome back. So let's start this compliance topic with Bruker's philosophy, innovation with integrity. I think this fits perfectly to this topic, yeah, because especially in pharma industry, innovation is important, but integrity, like data integrity, is as well very important. Yeah, so I want to emphasize that, for example, such things like GC, GMP, 21 CFR Part 11 cannot just be specifications on a spec sheet. Yeah, of course, there are always responsibilities on us as equipment manufacturer, but of course as well you as user, you have responsibilities, and it's clear ultimately at the end it's your owner user being responsible that an instrument, for example, is qualified properly. So our advice is always review a solution in detail. Yeah, can a supplier give adequate support for instrument qualification? Later on, yeah, the method setup, validations. Is there adequate programs for performance testing and maintenance programs and services available? That's all important topics. Yeah. So, but let's start from the very beginning. Yeah. Before there's a purchase of an instrument or something like this. Yeah. You need to qualify us as suppliers. User requirement specifications need to be drafted, which not only consider, for example, the analytical technique, but everything around it. Yeah, all IT topics and pharma compliance topics need to be considered. That's clear. And then, of course, you need to draft design qualification where you need to show that an instrument is suitable for the intended application. And at that point, a manufacturer needs to support as well. Yeah, it's in his responsibility to provide design specification, functional requirements, have a program, quality systems in place and programs for acceptance testings in order that we can ensure and deliver a robust instrumentation. But the latest with installation qualification, from our standpoint, comprehensive support in means of validation support from service or validation documentation is really an essential topic in order to qualify an instrument properly. Just for example, in our installation qualification procedures, the main steps which we are consider is, of course, safety, operator safety. That's an important aspect. Of course, we need to review the installation site requirements if they are fulfilled. All components need to be identified and documented properly. The hardware, let's say the spectrometer system, needs to be installed properly. Computer system installed. Then there are, of course, software installation, for example, the vibrational spectroscopy software Opus, and everything needs to be connected and prepared and, of course, properly documented. And here the experience and support from a vendor is a very essential point. Especially then it comes to the operational qualification, where we check all the functionality of hardware and software. There's a lot of documented testing requirements required, and at the end as well, performance testing according to pharmacopoeia requirements. This performance testing is then typically extended in the performance qualification, where we test in routine as well later on that our instrument is fit for the application. And this, of course, all needs to be documented. We have comprehensive test log forms where all these IQ/OQ procedures are well documented. But that's, of course, not all documentation which a vendor needs to provide. It's a large topic, compliance topics. And so what about quality management in software development? Software is a very crucial part nowadays of an instrument delivery. Are there software test protocols existing, certificates, if it's ISO certificates, software release protocols, validation and 21 CFR Part 11 compliance statements? Of course, we need to have as well a maintenance plan and concept prepared, including topics like backup and restore of data. And of course, all needs to be supported with software and hardware manuals, and such documentation sums up basically to a lot of paperwork at the end, where it's needed that a vendor can support properly. And in practice, for example, let's say the performance qualification of a device should be always verified in routine. For our vibrational spectroscopy techniques like Raman, mid-infrared spectroscopy, near-infrared spectroscopy, there are several relevant pharmacopoeia chapters which specify performance criteria which really needs to be tested and assessed on a routine basis. Just for example, with the handheld Raman spectrometer Bravo, we are testing all these pharmacopoeia requirements in our daily PQ test explicitly. We really determining the wave number accuracy, photometric consistency, spectral resolution, and photometric precision, which is required. And let's say alternative, rather simple system suitability approaches, which let's say only show a fit for purpose and not directly assess these parameters, should only apply if it's not otherwise possible. For example, if something, a probe, is in a closed process, you cannot take it just out and make let's say a reference measurement on a reference standard. And of course, these performance tests here are good topics, need to be done with, of course, certified and traceable reference materials, which we do supply with our instruments. Then, of course, one needs to have a data integrity concept. They are very important these days that things are follow the ALCOA Plus principle. So let's go quickly through this ALCOA, what this stands for. So data needs to be attributable. So It needs to be clear who measured a spectrum or did evaluate something. Yeah, typically there's a user management in the background. Yeah, we have an audit trail with time and date stamp. That's clear. Data needs to be legible, which means needs to be a permanent data storage, needs to be protected against unauthorized changes. Yeah, it needs to be protected against deletion and loss. And in our Opus software, we have the so-called protected data pool, and everything which is therein is basically protected from unauthorized manipulation. Things need to be recorded at the time when things have been generated. For example, this avoids, for example, previews where an operator could decide, that's a good or bad result, I want this or that. Of course, this needs to be avoided by design in a software. A very important aspect for vibrational spectroscopy is that the data needs to be original. And this points to the raw data, because spectroscopic data is dynamic data. You can do a lot of calculations based on this data. And in doing so, it's always important that the raw data is maintained and, for example, not overwritten. In Opus, we have this GLP mode function, which always retains the raw data, and all evaluations basically are performed on let's say, on a backup copy of the original raw data. A stands for accuracy. That's clear that things need to follow a strict workflow, enforced workflow. Our files have as well history blocks where everything is traceable. And of course, system tests need to monitor the instrument performance, that at any time one is sure that valid results are generated. The user management in today's software is as well important. Typically, there's a very easy solution for our customers, which is Active Directory support. Therefore, for example, password requirements automatically are fulfilled considering your IT guidelines. That's a very easy, straightforward, state-of-the-art method to do so. Of course, for a standalone user management, there's a little bit more to consider, that a software fulfills all these configurable password requirements, like, for example, the maximum number of invalid login attempts, password complexity requirements, password expiration need to be considered. Of course, inactivity log as well important. If things are left alone, that, for example, after 5 minutes, the application is locked. A software needs to support different user roles, like an administrator role for administrative tasks. And then there are operative roles like a lab manager role, or you can consider a lab manager as well as an advanced operator with higher education, and standard operator roles. And of course, these needs to be certainly fixed, at least between administrator and operative roles, to really enforce as well the segregation of duty. As well, an aspect where we come across here and there is that user ID and password authentication does not replace the need for electronic signatures. That's clear. So for example, in our Opus software, we can assign the right to do electronic signatures with configurable meanings to individual users. Of course, if these users then attach an electronic signature to an electronic record, there's of course an additional user ID and password authentication required. And of course, for these release categories like release and lock we do have in our software, we are enforcing a 4I principle for this such electronic signature, meaning before someone can do a release signature, there must be a review signature from a different person existing. And it's clear electronic signature shall not be deleted, or of course it needs to be avoided that these just can be copied from A to B. I think that's a clear requirement. Audit trails, they are as well very important today. In recent years, where we extended our Opus software very much the capabilities, because an audit trail should not be simply a log file. It's clear that an audit trail needs to log the relevant tasks like all the user management, electronic signatures, everything around electronic records, so the measurement, data evaluation, the setup of analytical methods, their changes, so change parameters need to be logged. And to date, for example, we have all this information in a database, which makes this really easily accessible for review. For example, we have it in a database, so you can simply filter according to date and time. You can filter according to activity, according to user. So that's very easy for review. And perhaps as well, nice to mention, if you have a measurement file from the Opus software, it includes its own audit log. Directly from a file, one can have a look at an history, and one can see what happened to this file, who processed something, who did some evaluation, and things carry as well an universal object ID, GUID, how you typically know it, so that we can really clearly identify files and assign it to a certain system. Yeah, with that, my contribution here is finished. And let's open the Q&A session. Right. We have the 2 questions. I will just have a look at them and read them.
Yeah, actually, I can read them. So one of the questions is, what algorithm is used for comparing two spectra? So I think the question is directed at Mario for his quality control.
Okay, so I cannot go into the specifics of the mathematical algorithm behind that, but in principle, it's just really the system breaking down the spectra you can imagine into numbers and then comparing those with the numbers in the library. And from there, basically calculating the hit quality. That's usually for us, it's done in a straight number from 0 to 1000. But others can also use in percentage-wise. And from there, you always get basically the best hit. But obviously, it's never 1000 because there are some numbers not perfectly fitting due to some background noise, which is always there. But in general, if it's the same spectra and the peaks are the according number, the according absorption, as I said, fingerprint, you will always get a hit and perfect if the numbers are perfectly aligned.
Okay, thank you, Mario. So actually, there's another question coming from another guest. So
Sure.
he or she asked, how can we find the library spectrum? So I guess he's asking, where do you find the library spectrum? Probably is it from Bruker, or do they have to create their own library? And the second question the person has is, and how about the confidence level the library spectrum is used for comparison?
Okay, to the first part, usually the libraries, if you purchase one from us or others, there are also library providers out there. Those libraries are protected in general. So you cannot really pick out the spectra out of that. The software in itself will look in this library and then compare the spectra. However, there's also the possibility to create an additional library on top. And then if you want to compare spectra, you just select with which library the software shall compare your spectrum. Like you can select the ones you purchased or you created, and then you can add even further spectra, and then the software will compare your spectra with all those. And to the reliability, as I just explained, it's really highly reliable because it really tries to figure out the significant peaks. As there is a fingerprint, it's always like you can say 100% sure if it's one component. But for example, if there is a mixture, there's then another mathematical algorithm behind it, or an even AI trying to figure out calculating all those different spectra together. And from there, the reliability is still high, but sometimes might be checked from an expert for the mixture analysis. As I said, there are results given in a hit quality or percentage quality. And from that, you can already see if it's a really high hit. So the reliability is also very high for this.
Okay, thank you, Mario. There is actually one question now. Comparing IR spectrum by visual, how much deviation can be accepted?
This is well, sometimes depending on the spectra in itself. because, for example, if you look, especially with polymers like low density and high density polymer, they are still really similar. So like if a deviation of like 2% sometimes will still result in the same spectra, and you get a notification that it cannot identify it correctly because, yeah, as I said, it's a density question and not a vibration because it's the same molecule. But in general, we can go down to 4% deviation. Like if you go to 96%, that's the rough estimation we aim for. And you can also, depending on how sure you are, modify methods in a way that you can say for these special molecules, for example, as I said, polyethylene, that you can say those are already verified at, for example, 94%, because there it's the difference between even the densities is higher. But usually 96% is the way to go.
Thank you, Mario. So I think we have a further question. How do you know, I think this is for Felix, how do you know that for your packaging material, whether it interferes with the material spectrum when you scan directly onto your material?
Okay, so beforehand, yeah, you most probably don't know. Of course, with our experience, we can typically guess, yeah. So with the handheld spectrometer, yeah, packaging contribution is typically always there. It's not a confocal setup like with the microscope where we can precisely define from what depth profile we are receiving the resolution. So this is basically part of the method setup and method validation, yeah, where we are assessing the influence of the packaging material. Yeah, for most cases, yeah, for example, PE packaging foils, yeah, the signals are very, very weak. As well, the signals from the glass, there's just fluorescence coming back, basically, which is suppressed by SSE. And then there are further possibilities, of course, in the method setup. Yeah, we can restrict spectral ranges. We can focus, let's say, on the vibrational bands of the material of interest. And like this, one can basically suppress the influence from the packaging. Yeah? So, but typically for most of the materials, it's less of a concern as the contribution is minor.
Thank you, Felix. Maybe we just wait another 1 or 2 minutes in case some of the audience is trying to type in the questions. We have one question coming out. The question is, can you use the result of content uniformity by Raman to replace the result from the method that was mentioned in the model graph of pharmacopoeia? Do we need validation or only verification is enough?
Of course, yeah, there are as well approaches for content uniformity studies with Raman spectroscopy. Yeah, at Bruker, we have a rather broad portfolio of instruments like with techniques, NIR spectroscopy, IR spectroscopy, Raman spectroscopy. And typically, I would say for most applications we have here, it's a playground of NIR spectroscopy. So this is where we do really the real authentication, quantification, and we have really good, the best experience here. That's why we are following up here with NIR spectroscopy mostly. But of course, it's as well possible with Raman spectroscopy. Perhaps Mui, you want to spend as well a few words on that topic?
Well, for NIR spectroscopy, because it is a secondary method and it's a multivariate calibrations, for sure that is first validation when you develop a model, but then it is often required, I think, even by the pharmacopoeia, that you need to have a certain number, which is called a second validation set, to make sure that when we are predicting it on the totally independent samples, then it works and it have an error within the acceptable range.
Thank you, Mui, and thank you, Felix. So I hope it answers your question. Is there anyone who want to add on any further questions before we close the session?
So again, thank you very much to the speakers. And Yuan, I think we can wrap it up here. Okay. 8 minutes early. So wishing everyone a good weekend ahead.
Thank you,
Thank you very much.
Christina.
you.
Thank you, Felix. Thank you, Mario. Thank you, Mui.
Thanks.
Thank you
Yeah,
very much.
all attendees, for sure. And have a great
Okay.
day.
Have a great day. Bye bye.
Bye bye.